Have you ever paused to truly observe the invisible forces that shape our everyday world? I mean, think about it. From the comforting warmth of a hot cup of coffee to the steady, almost silent hum of your refrigerator, or, the power generated by an engine, energy is constantly at work.
It really is. It's transforming, moving, dictating how everything functions.
Exactly. But beneath these familiar experiences lies this sophisticated set of fundamental rules, thermodynamics, that govern every single one of those energy exchanges.
Yeah, it's kind of amazing, isn't it? We rely on these principles constantly, often without a second thought. The very comfort of our homes, the efficiency of our cars, industrial processes, they're all intricately woven into these fundamental laws.
Absolutely, and that's exactly what we're peeling back the layers on today. This deep dive is all about engineering thermodynamics. Our mission, really, is to illuminate the profound science behind heat, work, and, other forms of energy, showing you how they interact with matter. It's a journey into the foundational principles that quite literally power our modern world. And hopefully by the end, you'll see the mechanics of energy in a whole new light.
And we're thrilled to be your guides on this exploration of the fascinating world of energy here on the Deep Dive, presented by Knowledge Flow.
So to kick us off, for someone who maybe knows the general idea of energy, what is thermodynamics really? Is it just about things getting hot or cold?
Well, temperature and heat are definitely central, yeah. But thermodynamics is far more comprehensive than just that. At its core, it's the science that deals with heat, work, and various other forms of energy, chemical, electrical, mechanical.
Okay.
Along with the observable properties of matter that are related to them. Its primary focus, you could say, is on the conversion of heat energy into mechanical energy, and critically, the reverse.
Like a steam engine.
Yay!
Turning heat into motion.
Exactly. Imagine a steam engine turning heat from burning coal into the mechanical motion of a piston. Or conversely, a refrigerator using mechanical work to move heat. It's all about how energy shifts forms and, where it goes.
And when we talk about these systems, are we zooming right down to the atoms themselves? Or are we looking at the bigger picture? How does thermodynamics handle that micro versus macro scale?
That's a really crucial distinction. Thermodynamics fundamentally concerns macroscopic or large-scale changes and observations.
Okay, large scale.
Yeah. We're interested in the bulk behavior of matter, think pressure, temperature of a gas in a cylinder, rather than trying to track the incredibly intricate dance of individual atomic behaviors.
So if you're designing something like an engine or, say, a sophisticated climate control system, understanding this microscopic view is absolutely key. You're not worrying about every single molecule, just the overall effect.
Precisely. It kind of simplifies the problem considerably, doesn't it? It provides the framework for engineers to model and predict the behavior of entire systems without getting completely bogged down in the, frankly, unfathomable complexity of individual particle interactions. It's what makes practical application possible.
We've talked about what thermodynamics is, this, grand science of energy. But to actually put it to use, like building that engine or designing the climate system, you can't just look at the entire universe, right? You need to kind of draw a box around what you're studying.
Yes, exactly.
How do engineers define that crucial slice of the universe, the part they're interested in?
That's precisely where the fundamental concept of a thermodynamic system becomes our first absolutely indispensable tool. We define a thermodynamic system as a specific quantity of matter with a fixed mass and identity that we choose for our investigation.
So it's the thing we're focusing on.
It's the portion of the universe we are laser focused on, yeah.
And then everything else. That's just the surroundings.
That's right. Everything external to that chosen system constitutes the surroundings. And the interface separating the system from its surroundings, that's what we call the system boundaries.
Boundaries.
And these boundaries are interesting because they can be either movable, think like a piston in a cylinder, or fixed, like the rigid walls of a container.
So for thermodynamics, the universe is just the system plus its surroundings, a very contained view.
Indeed, it simplifies things. To illustrate this, let's take that classic example. Imagine gas contained within a cylinder sealed by a piston.
Okay.
We'd consider the gas itself as our system. Now, if we heat the cylinder from below, the temperature of that gas will increase. And what happens?
The gas expands, pushes the piston up.
Right. The gas expands and pushes the piston upwards.
So when the piston moves, the boundary of our system, the gas also moves. It's a movable boundary.
Exactly.
And if heat is coming in and work is being done by the gas pushing the piston, that energy is crossing the boundary.
Exactly right. During this process, heat is entering our system from the surroundings, and work is being done by the gas as it pushes the piston up. So both heat and work are crossing that system boundary. But here's the key point. Even though energy is crossing, the mass of the gas itself, our system, remains identifiable and fixed. We're still studying that specific quantity of gas.
Got it. So that piston cylinder setup sounds like what you'd call a closed system. Does that mean there are other ways a system can interact with its environment?
Absolutely. There are 3 distinct types of thermodynamic systems, and they're classified by how they interact with their environment, specifically in terms of mass and energy exchange. We just touched on the closed system.
Right. Energy in or out, but no mass.
Correct. A closed system exchanges energy like heat or work, but not mass with its surroundings. A sealed pressure cooker on a stove is a perfect example. Heat enters, the pressure builds, but no steam escapes, no mass crosses the boundary.
Okay, closed system. What are the other two?
Then we have the open system. This is a system that exchanges both mass and energy with its surroundings. These are incredibly common in the real world, actually.
Like us, humans.
Yeah, a human body is a great example. We take in food and oxygen, that's mass, and we release waste and heat, that's mass and energy. Or think about a flowing engine where fuel enters and exhaust gases exit, along with heat and work exchanges. The boundaries of an open system are always permeable to mass.
It makes sense. And finally, the most restrictive scenario.
That would be the isolated system. Now, this is more of a theoretical ideal. It's a system that neither exchanges mass nor energy with its surroundings.
Completely cut off.
Completely. Imagine a perfectly insulated, perfectly sealed container that truly allows nothing in or out. In reality, truly isolated systems are pretty much theoretical constructs. There's almost always some minuscule interaction, right?
Sure, perfection is tough.
But the concept itself is invaluable for theoretical modeling and for understanding limiting cases.
You know, it seems really clear why distinguishing between these system types, open, closed, isolated, is the very first fundamental step in analyzing any real-world thermodynamic problem if you get this wrong at the start.
Your entire analysis could be flawed. Precisely. It dictates which conservation laws apply and how we apply them. For an isolated system, both mass and energy are conserved within its boundaries.
Okay.
For a closed system, mass is conserved within the boundary, but energy can cross it.
Right.
And for an open system, neither mass nor energy within the system is necessarily constant because stuff is flowing in and out. That significantly changes the mathematical approach you need to take for analysis.
That makes perfect sense. So we've talked about systems defined by a fixed amount of mass. But what about situations where there's a continuous flow, like water through a pipe or air through a turbine? That's where this idea of control volume comes in, isn't it?
You're exactly right. The concept of a control volume shifts our perspective. Instead of tracking a fixed quantity of mass as it moves around.
Like following one specific puff of air.
Right. Instead, we observe a fixed region in space. A control volume is a defined volume through which mass, heat, and work can continuously flow in and out across its boundaries.
So the control surface would just be the boundary of this fixed volume, like the inside walls, the pipe section we're looking at.
Yes, the control surface is simply the boundary of the control volume. And a critical point here is that the mass within that control volume might not be constant over time.
Okay.
Especially when fluids are flowing continuously in and out, mass could accumulate inside the volume or it could deplete. It depends on the flow rates.
That's definitely a different way to think about it compared to the fixed mass of a closed system. Can you give us a practical example?
Sure. A great example is an air compressor running continuously. Air is constantly entering the compressor through an inlet, it gets compressed inside, and then it exits through an outlet. The physical space of the compressor itself, that fixed region, is our control volume. We're not trying to track individual air molecules on their journey. We're observing the net flow of mass and energy across the compressor's fixed boundaries over time.
I see. It's kind of like observing traffic patterns at a fixed intersection rather than trying to follow one specific car on its entire journey from home to work.
That's an excellent analogy. Yeah.
You're focused on what crosses a defined spatial boundary, not the history of a specific piece of matter.
Exactly. And this approach allows for what we call steady-state analysis of devices where mass is continuously flowing, which is absolutely crucial for analyzing things like power plants, jet engines, pumps, turbines, lots of engineering hardware.
Okay. So once we've defined our system or our control volume, we then need to talk about what happens inside them. This brings us to the dynamics of change. Properties, states, processes, and cycles. Let's start with the different phases of a substance. We all know water exists as solid ice, liquid water, or vapor steam.
Right. A phase is essentially a quantity of matter that is homogeneous throughout. So a block of ice is one phase, a puddle of water is another, and steam is a third.
Uniform stuff.
Uniform stuff, exactly. And if you have multiple phases present at the same time, like ice floating in water, they are separated from each other by what we call phase boundaries.
So ice water has two phases and one phase boundary where they meet. Got it.
Yeah.
Now, what defines the state of a substance?
A state is the specific condition of a substance, and it's identified by its observable macroscopic properties, things like temperature, pressure, volume, density. For a given pure substance, if you know a few of these key properties, you've essentially defined its exact condition, its state, at that moment.
And when those properties change, that's what you call a process.
Precisely. Whenever there's a change in one or more properties of a system, that signifies a change in state. And the journey, the path from one state to another is called a process.
Okay.
Let's go back to our piston cylinder example. If we remove some weights from the piston,
the pressure inside drops.
Right. The pressure inside the cylinder decreases and the gas expands, so its volume increases. This leads to a new state for the gas, lower pressure, higher volume. The expansion itself is the process. A process is essentially the path that a system takes through a succession of these different states.
And then what's a cycle? Sounds like it comes back around.
That's exactly what it is. A cycle is a series of processes where a system ultimately returns to its initial state.
Back to square one.
Back to square one. This means that after undergoing several transformations, all its properties, temperature, pressure, volume, internal energy, everything, resume their original values that they had at the very beginning of the cycle.
So a real-world example of a thermodynamic cycle would be something like the circulation of steam and water through a steam power plant.
Absolutely. That's a perfect illustration. Water is heated to become steam.
High pressure, high temperature.
Right. It expands through a turbine to do work. Then it cools down and condenses back into liquid water. And finally, it's pumped back to the boiler to be reheated and start all over again. That continuous loop where the working fluid returns to its original condition is a thermodynamic cycle.
You know, understanding these terms, system, state, process, cycle, it really is like learning the grammar of thermodynamics. It gives us the precise vocabulary to discuss these complex energy transformations.
It does. It allows you to read and write about energy transformations clearly.
And to actually measure and calculate all these changes, we rely on a specific set of variables and units. We're all familiar with the core measurements in physics, mass in kilograms, length in meters, time in seconds. But in thermodynamics, temperature, specifically in Kelvin, becomes particularly vital, right?
Yes, absolute temperature in Kelvin is crucial. And from these fundamental variables, mass, length, time, temperature, we derive all our secondary variables. Things like volume, cubic meters, density, kilojoules, cubic meter, force, newtons, work and energy, joules, power, watts. These are the real workhorses for our calculations.
These units are the bedrock, aren't they? They ensure precision in our understanding and allow us to actually quantify everything. Without these standardized measurements, talking about energy transformations would just be hand-waving.
It would be purely qualitative. These units allow for quantitative analysis, which is essential for engineering.
Okay, now let's get into the laws themselves, the fundamental rules that govern all these energy transformations we've been talking about. And we start with a seemingly simple, but actually really crucial one, the Zeroth law of thermodynamics. But first, maybe we should clarify, what's thermodynamic equilibrium? It sounds like a state of perfect balance.
It is indeed a state of perfect balance. Thermodynamic equilibrium is the condition where the properties of a system, like its temperature, pressure, entropy, you name it, remain unchanged over time.
Stable.
Stable. To visualize this, imagine taking two different bodies, A and B, initially at different temperatures. Let's say body A is hot, body B is cold.
Okay.
When they come into contact, what happens? Heat starts transferring from A to B.
Right. The hot one cools down, the cold one warms up.
Precisely. And eventually, after some time, both bodies will reach the same constant temperature. They'll stay at that temperature indefinitely if left alone. At that point, they've attained a state of thermal equilibrium. When a system is in thermodynamic equilibrium, there are no spontaneous changes happening within it. It will remain in that condition unless disturbed.
And for a system to truly be in thermodynamic equilibrium, there's specific conditions that must all be met, right? It's not just about the temperature being the same everywhere.
That's a critical point, yes. A system must satisfy all three of the following conditions to be truly in thermodynamic equilibrium. First, there's thermal equilibrium.
Same temperature.
Right. That means the system or two bodies in contact have the same uniform temperature throughout. There's no net heat transfer occurring because of temperature differences.
Okay, so temperature has to be perfectly even. What's next?
Second, chemical equilibrium. This is the state where there's no tendency for chemical reactions to occur within the system, and also no net movement or diffusion of different types of atoms or molecules from one area to another.
So no reactions, no mixing going on.
Essentially, yes. Think of a perfectly mixed gas that isn't reacting, that's in chemical equilibrium. All the sort of drivers for chemical change, what we call chemical potentials, are balanced.
Makes sense. And the third condition?
The third is mechanical equilibrium. This means pressures are uniform throughout the system, and there are no unbalanced forces acting within the system or between the system and its surroundings. If there were any unbalanced forces, things would move or change until they balanced out.
So a system must satisfy all three, thermal, chemical, and mechanical equilibrium, to be truly in thermodynamic equilibrium.
Yeah.
If even one of these conditions isn't met, it's considered to be in a non-equilibrium state.
That's correct. And it was based on this understanding of equilibrium, particularly thermal equilibrium, that the Zeroth law was proposed by the British physicist Ralph H. Fowler.
Okay, so what's the elegant statement of the Zeroth law itself?
It states, quite simply, if two systems are at the same time individually in thermal equilibrium with a third system, then these two systems are also in thermal equilibrium with each other.
Huh. So if system A is the same temperature as system C, and system B is also the same temperature as system C,
right,
then A and B must be the same temperature as each other. Meaning, if you brought A and B into contact, no heat would actually flow between them.
Exactly.
You know, that sounds almost trivially obvious, but it's actually profound. This seemingly simple rule is the quiet enabler of modern temperature measurement. Without it, how could a thermometer work reliably?
Yeah.
We wouldn't have a universal sameness of temperature to compare against.
It absolutely underpins the concept of temperature measurement. It establishes temperature as a fundamental measurable property that indicates thermal equilibrium. Without the Zeroth law, the concept of a reliable thermometer, something we take for granted, wouldn't really hold up logically.
Wow. Okay. Now, let's talk about the big one, the one most people have probably heard of. The first law of thermodynamics. This is all about the conservation of energy, right?
Yes, this law is foundational. It's built directly on that fundamental principle of conservation of energy. The idea that energy cannot be created or destroyed, it can only be transformed from one form to another.
So if you supply heat to a system, it doesn't just vanish, right?
Yeah.
And it doesn't all get magically converted into useful work with 100% efficiency either.
Precisely. That's the key insight. When heat is supplied to a system, it's not all converted into work. A portion of that heat energy is used to perform external work, like pushing that piston up, and the rest goes into increasing the internal energy of the system's molecules. Think of it like an energy budget.
Okay.
The heat supplied, the income, has to go somewhere. It's either spent on doing work, expenses, or it increases the internal energy savings.
Right, the energy bank account inside the system.
Yeah.
And there's a neat mathematical formulation for this budget.
Yes, the core equation is elegantly simple.
Yeah.
HU plus AU.
Okay, let's break that down.
Yeah.
AQ is?
AQ represents the heat energy supplied to the system.
Okay.
And AQW is the work done by the system on its surroundings.
Yeah.
And AU is the change in the internal energy of the system itself.
So the heat you put in either comes out as work done by the system, or it's stored inside the system as an increase in its internal energy.
Exactly. Or you can rearrange it. The change in internal energy is equal to the heat energy given to the system minus the work done by the system. So AUQ, FUW.
Makes sense.
This law directly implies that heat energy can be converted into mechanical energy, and conversely, mechanical energy can be converted back into heat. For gases specifically, when a small amount of heat, let's call it dQ, is supplied, a part of it, let's call it W, is utilized for doing external work, and the remainder, dE, increases the internal energy of the gas. So we often express it infinitesimally as dQ plus W. This is sometimes called the gas energy equation.
So, for you listening, this first law is truly the bedrock of all energy calculations. It's why we can't get something for nothing in terms of energy. It's always accounted for, always conserved, even as it transforms between heat, work, and internal energy. It sets the fundamental boundary conditions for all energy interactions.
Indeed. No perpetual motion machines of the first kind, as they say. No free lunches in the universe, thermodynamically speaking.
No free lunches. I like that. It feels like thermodynamics is the universe's ultimate accountant, always making sure the books balance, even if the outcome isn't always what we'd prefer. Now, let's talk about specific thermodynamic processes. These are the key types of transformations that systems undergo. You mentioned there are 4 primary types.
Yes. The main ones we focus on are adiabatic, isothermal, isobaric, and isochoric processes. Each one defines a specific condition that's held constant during the change.
Let's start with isothermal change. What defines this one? The name sounds like same temperature.
You got it. An isothermal change is defined by a change in pressure and volume that occurs at a constant temperature. Imagine our cylinder and piston again. But this time, the cylinder walls are made of a really good conducting material, letting heat flow easily. If you slowly compress the gas...
The temperature would normally rise because you're doing work on it.
Right, but because the cylinder is conducting and you do it slowly, the excess heat generated is immediately transferred out to the surroundings. This keeps the gas temperature constant.
So the temperature doesn't actually rise, it stays put. And if you expand the gas slowly instead...
Same idea, but in reverse. If the piston moves upwards and the gas expands slowly, its temperature would naturally want to decrease, as it does work on the piston. But again, because the cylinder is conducting, it draws in just enough heat from the surroundings to compensate for that cooling effect, keeping the temperature constant.
Okay, so constant temperature is the key. What does that mean for the first law?
Well, for many substances, particularly ideal gases, internal energy depends only on temperature. So if the temperature is constant, there's no change in internal energy. Internal is 0.
So the first law, WW plus EU, simplifies.
It simplifies nicely to dQ over GW. In an isothermal process for an ideal gas, all the heat supplied is converted directly into work done by the system during expansion, or all the work done on the system comes out as heat during compression. And for an ideal gas undergoing an isothermal process, the simple relation PV equals constant holds true, or P1V1 equals P2V2.
Got it. Next up, adiabatic change. Now this sounds like the opposite of isothermal in terms of heat exchange. Adiabatic means no heat transfer, right?
Yeah, exactly. An adiabatic change is a process where there is no heat whatsoever entering or leaving the gas. dQ equals 0.
Okay.
Think of the same cylinder and piston, but this time both the cylinder walls and the piston are made of perfect non-conducting material, like thick insulation. And crucially, the compression or expansion happens suddenly, very quickly.
Suddenly? Why suddenly?
Because if it happens quickly, there's no time for any significant heat transfer to occur, even if the insulation isn't perfect. So if you suddenly compress the gas...
Work is done on the gas, but the heat can't escape.
Precisely. So the temperature must increase rapidly. The work done on the gas goes entirely into increasing its internal energy, raising its temperature.
And if it expands suddenly?
Conversely, if the piston moves upward suddenly, the gas expands and does work by using its own energy. Since no heat can flow in to replenish that energy, the work is done entirely at the cost of its internal energy. Its temperature drops significantly.
So for an adiabatic process, what happens to the first law?
Since dQ equals 0, the first law becomes 0 equals dE plus W, or more commonly written as W equals dE, using E for internal energy here. The work done is directly equal to the negative change in internal energy. So in an adiabatic process, temperature definitely changes, but heat transfer is 0.
Okay, isothermal is constant temperature. Adiabatic is 0 heat transfer. What about the other two? Isobaric and isochoric processes.
An isobaric process occurs at constant pressure. Think bar, like barometer.
Okay, pressure doesn't change.
Right. On a pressure-volume diagram, this would just be a horizontal line. In this case, heat can be transferred, work can be done, EW, and internal energy can change, generally. All three are non-zero. The work done is particularly easy to calculate, though. Since pressure P is constant, WP times the change in volume, AV.
Can you give an example of isobaric?
A uncommon example is boiling water in an open saucepan on your stove. As the water boils and turns to steam, it expands, but the pressure remains essentially constant at atmospheric pressure.
Makes sense. And isochoric process, that sounds like constant volume.
Choric
like space or volume?
Exactly right. An isochoric process, sometimes called isometric or isovolumetric, occurs at constant volume.
So EV is 0.
Yes, and this is significant because if the volume change is zero, then no work is done by the system on its surroundings, or vice versa. Why? Because work in this context is fundamentally PV. If EV is zero, W must be zero.
So what does the first law look like for an isochoric process?
If W is zero, then the first law, EAQW, simplifies to AUQ. All the heat added to the system goes directly into increasing its internal energy, raising its temperature, usually, and any heat removed comes directly from internal energy.
Like heating gas in a sealed, rigid tank.
Perfect example. The volume can't change, so any heat you add just makes the gas hotter and increases its pressure.
You know, what's really striking here is how these fundamental conditions, constant temperature, no heat transfer, constant pressure, or constant volume, dictate precisely how energy gets partitioned between work and internal energy changes. Engineers must leverage these distinct behaviors constantly in their designs, right?
Absolutely. Understanding which of these idealized processes is dominant in a particular part of a real system, like a compressor stage, a combustion chamber, or a heat exchanger, allows engineers to model the system, predict its performance, and optimize its design, whether they're working on a tiny refrigeration cycle or a massive power plant.
Now, we've talked about these idealized processes, isothermal, adiabatic, etc., but are they always perfectly achievable in the real world? This leads us nicely to the concept of reversible and irreversible processes.
Yes, this is a really important distinction between theory and reality. A reversible process is a purely theoretical ideal.
An idealization.
Exactly. It's defined as a process where, after the system changes state, it can be returned to its exact original state by reversing the path, and, critically, the surroundings are also returned to their original state. This means all the variables, pressure, volume, temperature, retrace their values perfectly in reverse order, and there are absolutely no net changes in the work done or heat exchanged with the surroundings over the complete forward and reverse cycle.
So it's like rewinding a perfect movie, frame by frame, with absolutely no loss or change anywhere. What conditions would be needed for that?
For a process to be truly reversible, it must occur infinitesimally slowly, essentially passing through a continuous series of equilibrium states. We call this quasi-static. And there can be absolutely no dissipative effects, no friction, no viscosity, no electrical resistance, no inelastic deformation, and crucially, no heat transfer across a finite temperature difference.
That sounds impossible in the real world.
It is. Reversible processes are ideal conditions that cannot be fully achieved in practice. All real processes are inherently irreversible to some degree.
Why? What makes real processes irreversible?
Well, think about all the things we just said couldn't happen for reversibility. Friction is always present in moving parts. Fluids have viscosity, electrical currents generate heat, rapid changes cause turbulence and pressure waves, and heat always flows from hotter to colder objects, never spontaneously the other way across a temperature gap. Mixing two different gases is also irreversible. They won't spontaneously unmix. These are all sources of irreversibility.
So if all real processes are irreversible, why is the concept of an ideal reversible process still so incredibly useful? It seems like just a fantasy.
It's vital because it sets the absolute theoretical limit for performance. It defines the best possible outcome under ideal conditions.
Like a benchmark.
Exactly. When engineers design a real engine or a refrigerator, they know they can never exceed the efficiency or performance of a perfectly reversible process operating between the same conditions, like the same temperatures. It gives them a target to strive for, even if unreachable, and more importantly, it allows them to quantify how much inefficiency exists in their actual real-world system compared to the theoretical best.
So it tells you how much room for improvement there might be.
Precisely. Think of it as the thermodynamic speed limit for a given road. You know you can't legally or physically go faster, and it tells you how close your actual driving is to that limit. It helps engineers identify where the biggest losses are occurring and where to focus their efforts to improve real systems.
That's a powerful way to look at it. An ideal that guides practical improvement. Now, how do we visualize all these changes and processes? We've mentioned pressure and volume changing. That's where the pressure-volume diagram, or PV diagram, comes in, right?
Yes, the PV diagram is an incredibly powerful graphical tool in thermodynamics, especially for closed systems. Its primary purpose is to visualize the relationship between pressure and volume during a process, and crucially, to determine the work done by or on the gas.
And the work done is actually represented graphically on the diagram. How?
It is. The work done during a process involving a volume change from V1 to V2 is exactly equal to the area under the curve representing that process on the PV diagram.
The area under the line connecting the start and end states.
Precisely. You determine this area usually through graphical integration or calculus if you know the equation for the curve. It literally paints a picture of the work interaction. Positive area, expansion, means work done by the system. Negative area, compression, means work done on the system.
Let's quickly interpret a typical PV diagram then, thinking about those processes we just discussed. What does an isothermal process look like?
Okay, for an isothermal process in an ideal gas, we know PV equals constant. On a PV diagram, this plots as a hyperbola, a curved line sloping downwards as volume increases. Since temperature is constant, AU equals 0, so the heat added EE equals the work done, EW, which is the area under that curve.
How about an isobaric process? Constant pressure.
An isobaric process occurs at constant pressure. So on the PV diagram, this appears as a simple horizontal line. The work done is just the constant pressure P multiplied by the change in volume, EVV, which is visually just the area of the rectangle under that horizontal line.
Makes sense. And an isochoric process, constant volume.
An isochoric process happens at constant volume. So this shows up as a perfectly vertical line on the PV diagram. Since there's no change in volume, EV equals 0, 0, the area under this vertical line is 0. No work is done, W 0. Therefore, from the first law, all heat added goes directly into increasing the internal energy.
And the adiabatic process, where no heat flows. How does that look different from the isothermal curve on the diagram? They're both curves, right?
They are both curves, yes, but they're distinct. The adiabatic process, where no heat flows, AQ equals 0, means that the change in internal energy equals the negative of the work done, AU at a BU value. For an ideal gas, the relationship is PV, constant, where gamma is the ratio of specific heats, CPCV, which is always greater than 1.
Okay, PV constant versus PV equals constant for isothermal. What does that gamma do to the curve?
Because gamma is greater than 1, the adiabatic curve on a PV diagram drops more steeply during expansion or rises more steeply during compression than the isothermal curve starting from the same point.
Why is that steeper drop so significant? What does it represent physically?
It shows that for the same amount of expansion, same hockey, the pressure drops more during an adiabatic process than an isothermal one. This is because, in the adiabatic case, the work done comes entirely from the internal energy of the gas, causing its temperature to drop significantly, which further reduces the pressure. In the isothermal case, heat flows in to keep the temperature constant, propping up the pressure more.
Ah, okay. The system is working harder internally in the adiabatic case without any thermal support from outside.
That's a good way to put it. The gas cools down as it expands adiabatically.
You know, that's a huge aha moment for me. The PV diagram really turns these abstract concepts and equations into a clear, visual story of a system's journey through different states. You can literally see the work being done or consumed.
It really does. It transforms the equations into an intuitive graphic, which is invaluable for both understanding the fundamentals and for designing and analyzing real thermodynamic cycles.
Yeah.
The area enclosed by a complete cycle on a PV diagram, for instance, represents the net work done per cycle.
Okay, so the first law tells us energy is conserved, quantity is maintained. But as we touched on, it doesn't tell us which way a process will spontaneously go. It doesn't, for example, prohibit heat from flowing all by itself from a cold object to a hot object, even though we know that never happens. It almost seems like a huge gap in the first law. What was the critical observation that really forced physicists to say, wait, we need another law here?
That's exactly the issue the second law of thermodynamics addresses. The first law accounts for the quantity of energy, but it says nothing about the direction of spontaneous processes or the quality of energy. The critical observation was exactly what you said. Certain processes, while perfectly allowed by the first law in terms of energy balance, simply never happen in reality.
Like heat flowing from cold to hot spontaneously.
Right. Or like building a hypothetical engine that could take heat from, say, the ocean, a single source, and convert 100% of it into useful work with no waste heat rejected. The first law wouldn't forbid that, but experience showed it was impossible. This fundamental contradiction between what the first law allowed and what was actually observed led to the formulation of the second law.
And the core idea of the second law is?
At its heart, the second law states that heat does not transfer automatically on its own from a cold body to a hot one. For that to happen, some external drive, some form of work input must be applied.
So a refrigerator, for instance, needs to be plugged in. It has to consume electrical work to pump heat from its cold interior out into your warmer kitchen. It doesn't just happen passively.
Precisely. Without that external work input, The process, heat flowing from cold to hot, would never occur spontaneously. The second law defines this directionality.
And there are two sort of cornerstone statements of the second law, the Kelvin-Planck statement and the Clausius statement. They sound different, but get at the same core idea. Let's break those down.
They do. Let's start with the Kelvin-Planck statement. This one focuses on heat engines. It declares that it is impossible to construct a device, a heat engine, that operates in a cycle and produces no effect other than the extraction of heat from a single temperature reservoir and the performance of an equivalent amount of work.
Okay, translate that. You can't just take heat from one place like the hot engine cylinder and turn all of it into useful work, like turning the crankshaft.
Exactly. It means you can't have a 100% efficient heat engine operating in a cycle. Some amount of heat must always be rejected to a colder reservoir, a heat sink. For a heat engine to operate continuously, it needs a temperature difference between a high-temperature source, where it takes heat in, and a low-temperature sink, where it rejects waste heat. An engine simply won't work if the source and sink are at the same temperature.
Got it. Waste heat is unavoidable. Now, the Clausius statement, that one focuses more on refrigerators and heat pumps, right?
Correct. The Clausius statement asserts that it is impossible to construct a device operating in a cycle whose sole effect is the transfer of heat from a cooler body to a hotter body.
So again, translating, heat doesn't flow uphill from cold to hot all by itself. You need to do something to make it happen.
Precisely. You need an external work input. Your domestic refrigerator, consuming electricity to move heat from its cold interior, I guess 10 degrees C maybe, to the warmer room, say 20 degrees, is the perfect example of this law in action. The electricity provides the necessary work input.
What's truly fascinating, though, is how these two seemingly different statements, Kelvin-Planck about engines and Clausius about refrigerators, are actually logically equivalent. How does that work? If one is true, the other must be true.
They are indeed equivalent. You can show this by assuming one is false and demonstrating that this would automatically lead to the other being false as well. It's a neat logical proof.
Okay, let's try it. Let's assume the Clausius statement is false. What would that mean?
If the Clausius statement were false, it would mean we could build a hypothetical refrigerator or heat pump that transfers heat from a low-temperature reservoir, TL, to a high-temperature reservoir, TH, without requiring any work input. A perfect refrigerator.
Okay, so we have this magical, free heat pump moving heat uphill.
Right. Now let's combine this impossible Clausius-violating heat pump with a standard real heat engine operating between the same two reservoirs, TH and TL. The engine does what normal engines do. It takes in some heat, Kengen, from TH, produces some work, W, and rejects some waste heat, Klingen, to TL.
Okay, so we have the impossible heat pump pushing heat QL up from TL to TH for free, and a regular engine running between TH and TL, producing work W, and dumping heat Klingen down to TL.
Exactly. Now let's adjust the size or operating rate of the engine and the impossible heat pump so that the amount of heat the pump pulls up from TL, let's call it QL, is exactly the same amount of heat that the engine rejects down to TL. Q engine equals QL.
So the net heat transfer to or from the low temperature reservoir TL is zero. It's just passing through.
Precisely. The low temperature reservoir becomes irrelevant. It's neither gaining nor losing heat overall. Now look at the combined system, the impossible heat pump plus the engine. What is its net effect?
The engine takes Kengen from TH. The impossible pump puts QL into TH. The engine produces work W. And there's no net interaction with TL.
Right. So the combined device takes a net amount of heat, Kengen QL, solely from the single high-temperature reservoir TH and converts it entirely into work W.
Wait, taking heat from a single reservoir and converting it all to work, that violates the Kelvin-Planck statement.
Exactly. So, assuming the Clausius statement is false leads directly to a violation of the Kelvin-Planck statement. You can do the reverse logic too. Assume Kelvin-Planck is false and show Clausius must be false. Therefore, the two statements are logically equivalent. They are just different ways of expressing the same fundamental limitation on energy conversion and transfer imposed by the second law.
Wow, that's a really elegant piece of reasoning. It's like they're two sides of the same coin, fundamentally defining the universe's limits on what energy can do spontaneously. It really shifts the focus from just how much energy we have, first law, to its quality, its usefulness, and the direction things naturally want to go.
That's a perfect summary. The second law introduces the concepts of irreversibility, directionality, and the degradation of energy quality.
And flowing directly from the second law, particularly its connection to irreversibility, is the concept of entropy. This is a term many people find a bit abstract or mysterious. What exactly is entropy?
Entropy, usually denoted by the symbol S, is a thermodynamic property. It's often described, perhaps a bit loosely, as a measure of the disorder or randomness contained within a given state of a system.
Disorder. Like a messy room has higher entropy than a tidy one.
That's a common analogy, yeah. Another way to think about it, which might be more intuitive for engineers, is that entropy is related to the amount of energy within a system that is practically unavailable to do useful work.
Unavailable energy. So it's energy that's just too spread out or disorganized to be harnessed effectively.
Kind of, yes. Think about heat energy. Heat at a high temperature is more useful or available for running an engine than the same amount of heat spread out at a low temperature, closer to the surroundings. Entropy helps quantify this unavailability or spread outness of energy. It builds a bridge between the microscopic motion and arrangement of molecules and the macroscopic properties of the system we observe.
Okay, so it connects a tiny jiggling of atoms to the overall behavior.
Same.
Is there a way to quantify the change in entropy?
Yes. For a reversible process, the change in entropy is defined as the amount of heat, Q, added to the system divided by the absolute temperature, T, at which the heat transfer occurs. Period S is QT. The units are typically energy per unit temperature, like joules per Kelvin, JK, or kilocalories per Kelvin.
So adding heat increases entropy, and doing it at a lower temperature increases entropy more for the same amount of heat. How does temperature influence this disorder concept?
Well, think about it. When you add heat to a system, the kinetic energy of the molecules increases. They move faster and more randomly, so their motion becomes more disordered. That increases entropy.
Okay.
Now consider the temperature. At very low temperatures, near absolute zero, a system, like a perfect crystal, has a very high degree of order. Molecules are barely moving. So if you add a given amount of heat energy, Q, to this highly ordered, low-temperature system, it causes a relatively large increase in disorder, a significant jump in entropy, with T being small.
Right. A little heat makes a big difference when things are very still. What about at high temperatures?
At high temperatures, the system is already quite disordered. Molecules are bouncing around chaotically, so adding the same amount of heat energy, Q, brings about less additional disorder relative to the chaos that's already there. The change in entropy, with T being large, is smaller.
That makes intuitive sense.
Yeah.
But what's the really crucial statement about entropy, especially for isolated systems?
This is a cornerstone of the second law. For any process occurring in an isolated system, the total entropy of that system never decreases. It either increases for irreversible processes, which are all real processes, or, in the theoretical limit of a reversible process, it remains constant.
Never decreases. So does this mean the universe, which we can consider an isolated system, is constantly heading towards more disorder, more randomness, less available energy?
From a thermodynamic perspective, yes. That's the implication. In any spontaneous process occurring within the universe, the overall entropy tends to increase. This ongoing increase in entropy suggests a constant movement towards a state of greater disorder and less available energy for work on a cosmic scale. It's often referred to poetically as the arrow of time entropy increase marks the forward direction of time.
That's a truly mind-bending thought, to ponder the universe slowly running down, thermodynamically speaking. And speaking of ultimate states of order, that brings us perfectly to the third law of thermodynamics. What does this one tell us?
The third law of thermodynamics provides a fundamental baseline, an absolute zero point, for entropy. Its core statement is that the entropy of a perfect crystalline substance is zero at the temperature of absolute zero, 0 Kelvin or negative 273.15 degrees.
So, at the coldest possible temperature imaginable, a perfectly ordered crystal has absolutely no disorder, zero entropy.
Precisely. At 0 Kelvin, theoretically, there's no thermal motion in the molecules of a perfect crystal. They are locked into a perfectly ordered lattice structure. Maximum order, minimum entropy, which the third law defines as zero.
And what happens as you warm it up from absolute zero? How does entropy change, especially thinking about phase changes? Let's imagine a temperature entropy diagram.
Okay. As the temperature rises just above 0 Kelvin, the average kinetic energy of the molecules begins to increase. They start to vibrate within the crystal lattice. This introduces a small amount of disorder, so the entropy gradually increases from zero as T increases.
So a slow rise in entropy as the solid heats up.
Right. Then, when the temperature reaches the melting point substance, a phase change occurs. The solid melts into a liquid.
Liquids are much more disordered than solids.
Exactly. The molecules have much more freedom to move around. This causes an abrupt increase in the entropy of the system at constant temperature as the latent heat of fusion is absorbed. You'd see a vertical jump on a TS diagram during melting.
And then as you heat the liquid.
As you continue to heat the liquid, its temperature rises and the molecules move even faster and more randomly, so entropy continues to increase gradually.
Until you hit the boiling point.
Right. When the temperature reaches the boiling point, another phase change occurs. Liquid to gas or vapor. Gas molecules have extremely high kinetic energy and move in a highly random, disordered fashion, occupying the entire volume available. This causes another, usually much larger, drastic increase in entropy at the constant boiling temperature as the latent heat of vaporization is absorbed. Another vertical jump on the TS diagram. After that, heating the gas further continues to increase its entropy.
So the third law, by setting that 0 point at 0K, provides a crucial baseline. It allows us to determine absolute entropy values for substances at different temperatures, not just changes in entropy.
Yes, it gives entropy an absolute scale. And it also implies that reaching absolute zero itself is practically impossible, as it would require removing all thermal energy and achieving perfect order, which becomes increasingly difficult as you approach 0K. It completes our fundamental understanding of energy, temperature, and disorder at their most basic levels.
Okay, so with all these foundational laws, 0, first, second, third, under our belt, let's transition into how thermodynamics actually works in action. We need to talk about the fluids that carry the energy and the practical systems that use them. First up, the medium of exchange itself, working fluids. What qualifies as a pure substance in thermodynamics?
A pure substance is defined as any substance that remains chemically homogeneous and has a fixed chemical composition even when its phase, solid, liquid, gas, or state temperature, pressure changes. Its chemical makeup doesn't vary throughout the substance.
So water, H2O, is a pure substance, whether it's ice, liquid water, or steam. It's all just H2O molecules.
That's a perfect example. And importantly, a mixture of ice and liquid water is still considered a pure substance because chemically it's all H2O.
Oh.
However, a mixture of, say, liquid air and gaseous air is also pure, if uniform, but a mixture of air, mostly nitrogen and oxygen and liquid water, is not a pure substance because you have different chemical species, N2O2, H2O, present.
Got it. Fixed chemical composition is key. Now, often in basic thermodynamics, we talk about an ideal gas. This sounds like a theoretical simplification, a building block.
It is exactly that. An ideal gas is a hypothetical gas used as a model. It's imagined to be composed of a large number of point particles or molecules that are in constant, random, straight-line motion.
Point particles, meaning they have no volume themselves.
Correct. The model makes several key simplifying assumptions. The molecules themselves behave as rigid spheres with negligible volume. There are absolutely no intermolecular forces acting between them. They don't attract or repel each other except during collisions. Collisions between molecules and the container walls are perfectly elastic, no energy loss, and the average kinetic energy of the molecules is directly proportional to the absolute temperature.
So essentially, they're tiny, perfectly bouncing, non-interacting particles. Why use such a simplified ideal model when real gases are obviously more complex, with real sizes and forces between molecules?
It's incredibly useful for developing the fundamental equations and understanding the basic relationships between pressure, volume, and temperature without the complications of real gas behavior. And importantly, many real gases do approximate ideal gas behavior quite well under certain conditions.
Which condition?
Particularly at low pressures where molecules are far apart and intermolecular forces are weak, and high temperatures where the molecule's kinetic energy is much larger than any potential energy of attraction. So using the simplified model helps us understand complex, real behaviors by giving us a baseline from which to measure deviations.
And this ideal gas has its own famous law, the ideal gas law.
Yes. The ideal gas law mathematically formulates the relationship between its main state variables, absolute pressure, P, volume, V, and absolute temperature, T. The equation is PV equals nRT.
Okay, PVT we know. What are N and R?
N is the number of moles of the gas, a measure of the amount of substance, and R is the universal gas constant. Its value is the same for all ideal gases, approximately 8.3145 joules per mole, Kelvin J mole in SI units.
PV, nRT. Got it. But as you said, real gases aren't always ideal. How do we bridge that gap? How do we account for the non-ideal behavior of real gases?
That's where the compressibility factor, Z, comes into play. It's a correction factor, a thermodynamic property that measures how much a real gas deviates from ideal gas behavior under specific conditions.
How is it defined?
It's defined as the ratio of the actual molar volume of a real gas, real, to the molar volume that an ideal gas would occupy, vidial, at the same pressure and temperature. So Z equals real vidial. Using the ideal gas law for vidial RTP, the formula is often written as Z equals real RT, where real is the specific volume per mole or per mass of the real gas.
So if Z equals 1 under certain conditions,
then the real gas is behaving exactly like an ideal gas under those conditions. Low pressure, high temperature usually. If Z is greater than 1 or less than 1, it indicates deviation from ideal behavior due to factors like molecular volume and intermolecular forces, which the ideal gas model ignores.
how do engineers figure out Z for different gases at different conditions? Is there a chart?
Yes, there is. It turns out that while different gases have very different properties, their deviation from ideal behavior is surprisingly similar when viewed relative to their own critical properties, specifically their critical temperature, Tc, and critical pressure.
Ah, the critical point. The temperature and pressure above which a distinct liquid phase can't exist, so we normalize using those.
Exactly. We define reduced temperature as Tr equals Ttc, the actual absolute temperature divided by the critical absolute temperature, and reduced pressure as Pr equals Ppc, actual absolute pressure divided by critical absolute pressure.
Okay.
By plotting the compressibility factor Z against the reduced pressure PR for various lines of constant reduced temperature Tr, we get something called a generalized compressibility chart. Amazingly, most gases fall roughly onto the same set of curves on this chart.
So you can use one chart to find the Z value for lots of different gases like ethane, methane, nitrogen, carbon dioxide, just by knowing their critical points and calculating Tr and Pr.
That's the power of it. It's a very practical tool for engineers to estimate real gas properties when detailed data isn't available, bridging the gap between the simple ideal gas model and complex real-world behavior.
That's really clever. Now, moving from the theoretical ideal gas, let's talk about one of the most historically significant and practically important working fluids, steam or vapor.
Indeed. Steam is simply water converted into its gaseous state, its vapor phase, typically by heating. Pure steam itself, by the way, is invisible. The white clouds we usually call steam are actually tiny droplets of condensed water mixed with the true vapor.
Right, and its historical significance.
It was arguably the first thermodynamic fluid to be widely harnessed for power generation. It was absolutely vital in the Industrial Revolution, driving the early steam engines and later steam turbines. Its properties have been studied extensively.
And how does its behavior compare to an ideal gas? Does PV and RT work for steam?
Not very well, generally. Steam behaves quite differently from an ideal gas, especially near its saturation point, where it's close to condensing back into liquid. It only starts to approximate ideal gas behavior when it's in a highly dried or superheated condition, far from condensation. Its properties are complex and usually require steam tables or specific equations of state for accurate analysis.
And you mentioned different conditions. There are specific types of steam, depending on how much heat has been added.
Yes, we usually classify steam into three main types based on its state relative to saturation. First, there's wet or unsaturated steam.
Wet steam.
Yeah, this is actually a two-phase mixture. It consists of gaseous steam mixed with tiny droplets of liquid water that haven't fully evaporated yet. Think of the mist just above boiling water.
Okay, then what?
If you continue adding heat to wet steam while keeping the pressure constant, eventually all those liquid water droplets will evaporate. At the point where the last droplet disappears, you have dry or saturated steam. It's pure H2O vapor at the saturation temperature for that pressure.
So 100% vapor, but just barely.
Exactly. And if you take that dry or saturated steam and heat it even more at constant pressure, its temperature will rise above the saturation temperature. This is called superheated steam. It's dry steam heated beyond its boiling point for that pressure. Superheated steam behaves a bit more like an ideal gas than saturated steam does.
Wet, dry, saturated, and superheated. Got it. Now, just a few more important thermodynamic properties or definitions related to fluids that often come up. Enthalpy, sensible heat, and latent heat. What's enthalpy? It sounds related to energy.
It is. Enthalpy H is a very useful thermodynamic property defined as the sum of the internal energy of a system plus the product of its pressure, P, and volume V. So the equation is H equals U plus PV.
Why combine internal energy and this PV term?
It turns out that this combination, U plus PV, frequently appears in the energy analysis of open systems, control volumes, involving flow. Defining enthalpy simplifies the energy balance equations for things like turbines, compressors, and heat exchangers, essentially grouping the internal energy and the flow work, PV term, together into one convenient property. Think of it as representing the total heat content or total energy associated with the fluid, including the energy needed to push it into or out of a control volume.
Okay, so it's a useful accounting property. Now, sensible heat. That sounds like heat you can sense, maybe with a thermometer?
That's exactly right. Sensible heat is the heat energy that, when added to or removed from a substance, causes a direct change in its temperature, but not a change in its phase.
Like heating water from 20 degrees C up to 90 degrees CD. The temperature rises, you can sense it getting hotter.
Perfect example. You're adding sensible heat.
So what happens when the water hits 100 degrees C and starts boiling? The temperature stops rising for a while, even though you're still adding heat. That's where latent heat comes in, right?
Exactly. Latent heat, meaning hidden heat, is the heat energy absorbed or released during a phase change, like melting, freezing, boiling, or condensing, that occurs without any change in temperature.
Hidden heat. Interesting.
While water is boiling at 100 degrees C at standard pressure, its temperature remains constant at 100 degrees C, but it's absorbing a significant amount of energy, the latent heat of vaporization, to break the intermolecular bonds of the liquid and turn it into steam, vapor. Similarly, when ice melts at 0 degrees C, it absorbs latent heat of fusion without changing temperature.
So that distinction is crucial. Sensible heat changes temperature, latent heat changes phase at constant temperature. Heating water to boiling involves adding sensible heat, while actually turning it into steam involves adding latent heat.
Precisely. Understanding both is fundamental to analyzing processes involving phase changes, which are central to many thermodynamic cycles like power generation and refrigeration.
All right, speaking of cycles, let's talk about the theoretical pinnacle of efficiency in heat engines, the famous Carnot engine cycle. Who came up with this?
The Carnot cycle is a theoretical, idealized thermodynamic cycle proposed by the French physicist Nicolas Léonard Sadi-Carnot back in 1824.
And its significance. Why is it so important if it's just theoretical?
It's hugely significant because it represents the most efficient possible cycle for converting a given amount of thermal energy, heat, into work, or conversely, for moving heat from a low to a high temperature using a given amount of work in a reversed Carnot cycle, like refrigeration. It serves as the ultimate theoretical benchmark for the maximum possible performance of any heat engine or refrigeration cycle operating between two specific temperature levels.
So it's the absolute best you could possibly do, the theoretical speed limit we talked about earlier. What's the underlying assumption that allows it to achieve this perfect efficiency?
The key is that the Carnot cycle consists entirely of reversible processes. It relies on the critical assumption of no wasteful, irreversible effects whatsoever.
So no friction.
No friction in any moving parts like the piston. No heat conduction between parts of the engine that are at different temperatures, except at the heat source and sink. No fluid viscosity. All processes must occur infinitely slowly, quasi-statically, to remain in equilibrium. It's a perfect, idealized scenario.
And how is it imagined to work? What's the setup?
Typically, it's visualized using an ideal gas as the working substance, contained within a cylinder fitted with a frictionless piston. The engine operates cyclically between two idealized heat reservoirs, one at a constant high temperature, TH, called the source, and one at a constant lower temperature, TL, called the sink. These reservoirs are assumed to have infinite heat capacity, meaning they can supply or absorb any amount of heat without changing their own temperature.
Okay, ideal gas, frictionless piston, perfect reservoirs. And the cycle itself consists of 4 specific reversible processes. Can you walk us through them?
Certainly. The cycle has 4 steps.
Reversible isothermal expansion. The gas starts at the high temperature TH. It's placed in contact with the hot reservoir, TH, and allowed to expand slowly. As it expands, it does work on the piston. To keep the temperature constant at TH during expansion, it must absorb an amount of heat. Let's call it Kin, or QH, from the hot reservoir.
Okay, absorbs heat, does work, stays hot, then.
Step 2. Reversible adiabatic expansion. The cylinder is now thermally insulated from both reservoirs. The gas continues to expand, pushing the piston further and doing more work. Since it's adiabatic, no heat transfer, this work is done at the expense of its internal energy. As a result, the gas cools down, dropping from the high temperature TH to the low temperature TL.
So expands more, does more work, cools down, now it's at the low temperature.
Right. Step 3. Reversible isothermal compression. The cylinder is now placed in contact with the cold reservoir, TL. An external force slowly pushes the piston inward, compressing the gas. Work is done on the gas. To keep the temperature constant at TL during this compression, the gas must reject an amount of heat, QOUT or QL, to the cold reservoir.
Okay, work done on it, rejects heat, stays cool. Final step.
Step 4. Reversible adiabatic compression. The cylinder is again thermally insulated. The external force continues to compress the gas. Since it's adiabatic, this work done on the gas increases its internal energy, causing its temperature to rise back up from the low temperature TL to the original high temperature TH. At this point, the gas is returned to its initial state, pressure, volume, temperature, completing the cycle.
4 steps. Isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. All perfectly reversible. And Carnot didn't just describe the cycle, he also derived some key principles about engine efficiency from it, didn't he?
He did. These are often called Carnot's principles or theorems. First, and perhaps most importantly, the efficiency of an irreversible, real heat engine operating between two given temperature reservoirs is always less than the efficiency of a reversible, like Carnot, heat engine operating between the same two reservoirs.
So real engines are always less efficient than the ideal Carnot engine. That makes sense due to irreversibility.
Yes.
What's the second principle?
The second principle is also profound. The efficiencies of all reversible heat engines operating between the same two temperature reservoirs are equal, regardless of the working substance or the specific design details of the engine.
Wow. So any perfectly reversible engine, whether it uses air, steam, or unicorn tears, will have the exact same maximum possible efficiency if it runs between the same hot and cold temperatures.
That's the idea. This maximum efficiency depends only on the temperatures of the reservoirs.
And this cycle can also be mapped onto a PV diagram, right? What does it look like?
Yes, it forms a closed loop on the PV diagram. You have the two isothermal curves, hyperbolas, connected by the two steeper adiabatic curves. The area enclosed by this loop represents the net work done by the engine during one cycle. Work net Stinkwout.
And the efficiency of this ideal Carnot engine has a remarkably simple formula based only on those reservoir temperatures, doesn't it?
It does. The thermal efficiency of a Carnot engine, denoted by Carnot, is given by GAT Carnot equals 1, TLTH, where TL and TH must be the absolute temperatures in Kelvin Rankine of the cold sink and hot source, respectively. It can also be expressed in terms of the heat transfers as gay, quicknet, kin, For a reversible cycle like Carnot's, it turns out that in a case is TLTH.
KL1, TLTH. That's amazing. Maximum efficiency depends only on how hot the source is and how cold the sink is. To get higher efficiency, you want TH as high as possible and TL as low as possible.
Exactly. That's the fundamental limit imposed by the second law.
But again, we have to stress, this is based on perfect reversibility.
Yeah.
It's almost impossible to actually build a real engine that perfectly executes this cycle due to the need for infinite slowness and the absence of friction and other losses.
That's correct. Real engines have many irreversibilities that reduce their efficiency below the Carnot limit.
So why is this purely theoretical engine still so immensely important for practical engineers? We touched on this benchmark idea.
It remains vital because it provides that absolute quantitative upper limit on efficiency. When an engineer designs or analyzes a real heat engine, like at a power plant or a car, they can calculate the Carnot efficiency for the temperatures it operates between. Comparing the real engine's actual measured efficiency to this, Carnot efficiency immediately tells them how well the engine is performing relative to the theoretical best possible. It's called the second law efficiency, or exergetic efficiency. It helps identify potential areas for improvement and guides the development of more efficient energy conversion technologies. It sets the gold standard.
A standard that pushes innovation. Okay, let's pivot now from engines generating power by moving heat from hot to cold to the opposite process, refrigeration cycles, which move heat from cold to hot. What's the fundamental meaning or goal of refrigeration?
Refrigeration, in simple terms, is the process of removing heat from a substance or a space under controlled conditions, thereby lowering or maintaining its temperature below that of the surrounding environment. It requires continuous heat extraction from the cold region.
So it's actively making something colder than its surroundings and keeping it that way. The device that does this is a refrigerator.
Correct. And conceptually, as you hinted earlier, a refrigerator is essentially a heat engine operating in reverse. Instead of taking heat from a hot source to produce work, it uses a work input to pump heat from a low temperature source, like the inside of the fridge, to a higher temperature sink, the surrounding room.
So it's actively pushing heat against its natural direction of flow, which requires work, as the Clausius statement demands.
Precisely. And the working fluid used within the refrigeration system to absorb heat at low temperature and release it at high temperature is called the refrigerant.
And the most common type of cycle used in our homes and in industry is the vapor compression refrigeration cycle. What are some common refrigerants used in these systems, historically and currently?
Historically, substances like ammonia, NH3, sulfur dioxide, SO2, and even carbon dioxide, CO2, were used. Over time, synthetic refrigerants like chlorofluorocarbons, CFCs, and hydrochlorofluorocarbons, HCFCs, became common, although many of those are now being phased out due to environmental concerns like ozone depletion. Newer refrigerants include hydrofluorocarbons, HFCs, and increasingly natural refrigerants like hydrocarbons, propane, isobutane, and CO2 again, but used in different cycle designs.
Okay. And how does this vapor compression cycle work in principle?
In this cycle, the refrigerant is continuously circulated through four main components. It undergoes phase changes alternating between evaporating, boiling at low pressure, and condensing back to liquid at high pressure. As it evaporates in the cold part of the system, it absorbs latent heat, providing the cooling effect. As it condenses in the hotter part, it releases that latent heat to the surroundings. This cycle is the workhorse behind almost all domestic refrigerators, freezers, and air conditioning systems, as well as large industrial cooling plants.
So it's all about managing the evaporation and condensation of the refrigerant at different pressures. Let's trace the four main processes the refrigerant goes through. It's often shown on a temperature entropy, TS diagram, or a pressure enthalpy, pH diagram. Let's outline the steps.
Okay, let's start after the evaporator.
Compression process. 1 to 2 on diagrams. The refrigerant leaves the evaporator as a low-temperature, low-pressure vapor. It enters the compressor where it is compressed, usually assumed to be adiabatically, or close to it, ideally isentropically constant entropy. This compression significantly increases both its temperature and pressure, typically turning it into a high-temperature, high-pressure, superheated vapor. Work input is required here.
So low PT vapor in, high PT superheated vapor out. Then it goes to the condenser.
Step 2. Condensation process, 2 to 3. This high-temperature, high-pressure vapor flows into the condenser. The condenser is essentially a heat exchanger where the refrigerant rejects heat to a cooler surrounding medium, like the air flowing over the coils at the back of your fridge, or cooling water in larger systems. As it rejects heat, the refrigerant condenses back into a liquid, usually at constant pressure. It typically leaves the condenser as a high-pressure, warm, but liquid, saturated, or slightly subcooled liquid. The latent heat of condensation is released here.
High PT vapor in, high P warm temperature liquid out. Next, it needs to get cold and low pressure again. That's the expansion valve.
Step 3. Expansion process, 3 through 4. The high-pressure liquid refrigerant then passes through an expansion valve, also called a throttling valve or capillary tube in small systems. This device causes a sudden, significant drop in both the pressure and temperature of the refrigerant. This is inherently an irreversible throttling process, where enthalpy ideally remains constant, but entropy increases. As the pressure drops below the saturation pressure, some of the liquid instantly flashes into vapor, resulting in a low-temperature, low-pressure mixture of liquid and vapor exiting the valve.
So high P warm liquid in, low P cold liquid vapor mix out. And finally, this cold mix goes into the evaporator to do the actual cooling.
Step 4. Vaporizing or evaporation process, 4 to 1. This low-pressure, low-temperature liquid vapor mixture enters the evaporator coils, the part inside the fridge or the AC unit. Here, it absorbs heat from the space or substance that needs to be cooled. This absorbed heat causes the remaining liquid refrigerant to evaporate, boil, completely into vapor, typically at constant pressure and constant temperature. It leaves the evaporator as a low-pressure, low-temperature, usually saturated or slightly superheated vapor, ready to return to the compressor and start the cycle over again. The useful cooling effect, the absorption of the latent heat of vaporization, happens here.
Compression, condensation, expansion, evaporation. A continuous cycle driven by the compressor's work input.
Now, how do we measure the performance or efficiency of this refrigeration cycle? You mentioned it's not called efficiency.
Right. For refrigeration and heat pump cycles, we use the coefficient of performance. That's the measure of the cycle's effectiveness.
And how's it calculated? COP is defined as the ratio of the desired output, the useful effect, to the required input, the energy cost. For a refrigerator, the desired output is the amount of heat removed from the cold space, evaporator or QL. The required input is the work done by the compressor, W compressor, or Winton. So, COP refrigerator, UL Winton.
Desired cooling effect divided by the work needed to achieve it.
Exactly. A higher COP means the refrigerator is more efficient, it removes more heat for the same amount of work input.
Okay, and here's that question again. Unlike the efficiency of a heat engine, equal Y naught QH, which is always less than 1 or 100%, the COP of a refrigerator can often be greater than 1. Why is that physical possible? It sounds like getting more out than you put in.
That's a great question, and it trips people up. It's because efficiency and COP are measuring fundamentally different ratios based on the purpose of the device. Heat engine efficiency compares the work output to the heat input, which is always larger. You're converting heat into work, and the second law limits this conversion. Refrigerator COP, however, compares the heat moved QL to the work input required to move it, Oyerdan. It's not about converting energy forms in the same way. You're using work W to pump an amount of heat QL from cold to hot. The first law tells us that the heat rejected to the hot side QH must equal QL plus W. The COP equals QLW. Since QL can definitely be larger than W, especially if the temperature difference TL and TH is small, the COP can easily be greater than 1.
So a COP of, say, 3 doesn't mean you created energy. It means for every 1 joule of electrical work you put into the compressor, the system successfully pumped 3 joules of heat out of the cold space.
Precisely. It's a measure of heat-moving effectiveness, not energy conversion efficiency in the heat engine sense. It's perfectly consistent with both the first and second laws. A good domestic fridge might have a COP in the range of 2 to 4.
That makes perfect sense now. It's about leverage using a little work to move a larger amount of heat.
Yeah.
Now let's quickly detail the actual physical components that make up this vapor compression system. You mentioned 4 main ones plus maybe a receiver.
Yes. The 5 primary components usually cited are the evaporator, compressor, condenser, receiver, often integrated or emitted in small systems, and expansion valve.
Let's start with the evaporator. What's its role?
The evaporator is the heat absorber. It typically consists of coiled pipes or plates located in the space or substance being cooled inside the fridge, the air handler of an AC. The low-pressure, low-temperature liquid vapor refrigerant flows through these coils, absorbs latent heat from the surroundings, and evaporates completely into a vapor.
Okay, that's where the cooling happens. Then the vapor goes to the compressor.
Correct. The compressor is the heart of the system, usually driven by an electric motor. Its function is to draw the low-pressure, low-temperature vapor refrigerant from the evaporator, suction side, and compress it to a high-pressure and high-temperature, discharge side. It then discharges this hot, high-pressure vapor to the condenser. It provides the work input needed to drive the cycle.
So the compressor boosts the pressure and temperature, and then this hot gas goes to the condenser.
The condenser is the heat rejector. It also usually consists of coiled pipes or fins located outside the refrigerated space, like the coils on the back or bottom of your fridge. The high-pressure, high-temperature vapor from the compressor flows through it. As it passes through, it transfers heat, both sensible heat from superheat and latent heat of condensation, to the surrounding cooler medium, usually air or water, causing the refrigerant to condense back into a high-pressure liquid.
Okay, rejects heat, turns back to liquid. And where does this liquid refrigerant go? Sometimes there's a receiver.
Yes, particularly in larger systems, a receiver vessel might be placed after the condenser. Its purpose is simply to store the condensed liquid refrigerant, providing a buffer and ensuring a steady supply of liquid to the expansion valve, even if the cooling load fluctuates. In many smaller systems, like domestic refrigerators, the receiver might be omitted or integrated into the condenser design.
Got it. Storage for the liquid. Which brings us finally to the expansion valve. What exactly does it do?
The expansion valve, or throttle valve, or capillary tube in simpler systems, has one primary critical function: to reduce the pressure of the high-pressure liquid refrigerant coming from the condenser down to the low pressure required in the evaporator. This pressure drop causes a corresponding sharp drop in temperature due to the throttling effect and flashing, making the refrigerant cold enough to absorb heat in the evaporator. It also regulates the flow rate of refrigerant into the evaporator to match the cooling load.
Fascinating how these 5 components work together in a continuous loop to achieve cooling. But you mentioned there's an alternative approach, especially useful in certain situations. The vapor absorption system. How does that differ?
Yes, the vapor absorption system achieves the same goal refrigeration, but uses a different method to create the necessary pressure difference between the evaporator and condenser.
How is it similar first? Does it still have an evaporator and condenser?
Yes, it shares the same core components for the heat transfer parts. It has an evaporator where the refrigerant boils at low pressure to absorb heat, and a condenser where the refrigerant condenses at high pressure to reject heat. The goal is still achieved through evaporation and condensation of a refrigerant at different pressure levels.
So where's the key difference then, if it doesn't use a mechanical compressor?
The primary distinction lies in how that pressure difference is created and how the refrigerant is circulated. Crucially, the mechanical compressor found in vapor compression systems is replaced by a thermally driven pump consisting of three main parts: an absorber, a generator, and a small solution pump.
Absorber and generator replace the compressor. How?
It works with two fluids: the refrigerant, often ammonia in older industrial systems or water in some AC systems, and an absorbent solution, like water for ammonia refrigerant or a lithium bromide salt solution for a water refrigerant.
Okay, two fluids working together.
Right. In the absorber, the low-pressure refrigerant vapor coming from the evaporator is absorbed into the liquid absorbent solution. This absorption process naturally maintains the low pressure in the evaporator, allowing the refrigerant to keep boiling at a low temperature. Think of the absorbent sucking the refrigerant vapor out.
So the absorber acts like the suction side of the compressor. Then what?
Then this rich solution, absorbent plus lots of refrigerant, is pumped by a small solution pump, which requires very little work compared to a compressor, to a higher pressure in the generator.
Okay, now it's at high pressure.
In the generator, heat is added. This is the main energy input, often from natural gas, steam, solar heat, or waste heat. This heat boils the refrigerant out of the absorbent solution. The refrigerant vapor is released at high pressure, ready to go to the condenser, just like after a compressor. The now weak absorbent solution, less refrigerant, flows back to the absorber to pick up more refrigerant vapor, completing the absorbent loop.
So the generator, using heat input, performs the compression and discharge function by separating the refrigerant at high pressure.
Exactly. And the liquefied refrigerant flows from the condenser through an expansion valve and back to the evaporator due to the pressure difference, just like in the compression cycle, completing the refrigerant loop. There are usually also heat exchangers added to improve efficiency by preheating the rich solution and pre-cooling the weak solution.
This sounds really clever.
Yeah.
It uses heat input instead of significant mechanical work input to drive the refrigeration cycle. Where might this be preferred over the standard vapor compression system?
Exactly. Its main advantage is that its primary energy input is heat, often low-grade heat. So vapor absorption systems are often economically favorable in situations where waste heat is readily available, from industrial processes, power plants, or solar thermal collectors, or where electricity is expensive or unavailable. They are common in large industrial refrigeration and large-scale air conditioning applications, though less common now in small domestic units compared to vapor compression.
What a journey we've taken. We've gone from just observing everyday energy transformations, the warmth of coffee, the hum of the fridge, to defining the specific systems and control volumes engineers use to analyze them. We explored the fundamental laws that govern all energy interactions, the Zeroth, first, second, and third laws, uncovering concepts like equilibrium, energy conservation, irreversibility, entropy, and absolute zero.
And then we saw how these abstract laws are ingeniously applied in practice.
Right. In crucial technologies like the theoretical benchmark of the Carnot engine and the very real workhorse cycles like vapor compression refrigeration that keep our food cold, and the alternative vapor absorption systems used in specific applications.
It's truly a testament, isn't it, how these seemingly abstract scientific principles, thermodynamics, underpin the very fabric of our engineered world, making so much of modern life possible.
Absolutely. So as we wrap up this deep dive, here's something for you to consider. Thermodynamics, which might seem like this abstract, maybe even intimidating science, actually provides us with a profound understanding of the fundamental limits and possibilities in our universe.
The rules of the game, essentially.
Exactly. It doesn't just inform the design of every machine that converts heat into work or moves heat around. It shapes our very understanding of phenomena like the arrow of time itself, this inevitable increase in universal disorder. This deep comprehension of energy's behavior continues to inspire innovation. How can we use energy more efficiently? How can we manage heat better? How can we push closer to those theoretical limits?
And that ongoing quest for efficiency and control over energy, driven by these thermodynamic principles, remains one of humanity's most critical scientific and engineering endeavors, especially today.
Thank you for joining us on The Deep Dive, presented by Knowledge Flow. We hope you view the world and the energy flowing through it perhaps just a little differently now.